Hello and welcome to this lecture. So, in this lecture, we are going to start looking at the definition of the derivative. Okay, so before we look at the definition very closely, I want to motivate it a little bit by zooming into this function f of x equals x squared at the point x naught equals 1. Okay, so this is the familiar y equals x squared curve. I have drawn this on Desmos. If you do that, you see, it starts at 0, it has this slow takeoff, and then it starts picking up and going higher and higher. At 1, the value is 1, at 2, the value is 4. I have zoomed into it. Okay, around x naught equals 1, I have zoomed into this function, this graph of this function, and the step on either side is 1. Okay, so what do I mean by that? Magnitude of step is h equals 1. I am zoomed into x naught equals 1. The step on the right side is 1. I have gone from 1 to 2, and the step on the left side is 1. I have gone from 1 to 0. And I have looked at the graph only in this interval, okay, 0 to 2. Step of 1 around 1, right? 1 is this, I go from 1 to 2 or 1 to 0. So, in that part, how does the graph behave? Okay. So, now what I am going to do here is this very interesting calculation. What is the calculation I am going to do? I am going to look at the right side and see how much the function has changed from 1 to 2. Okay. How much has the function changed when I went from x naught plus h to x naught? That is this difference, isn't it? F of x naught plus h minus f of x naught, and that is 3, right? Easy enough, 4 minus 1, 3. The function has changed that much. Now, this h is a thing here. Now, you may expect that, if h is very large, then the change will be larger. If h is very small, then the change will be smaller, things like that. So, instead of just looking at how much the function has changed, let me look at this ratio f of x naught plus h minus f of x naught divided by h. So, this one is sort of like a more interesting thing, and that is also 3 in this case because h itself is 1, right. So, it is easy enough. So, we can track this guy. Why exactly this guy? I gave you sort of a motivation, but there is also another motivation for why I want to look at this guy. So, this one is actually, if you join 1 comma 1 with 2 comma 4, right, if you join these two with a straight line, okay, this curve is also joining these two, but supposing I join 1 comma 1 and 2 comma 4 with a straight line, then this guy is the slope of that straight line, right. So, let me illustrate this with my own little diagram here. So, just to show you instead of showing on that picture. So, I have this y equals x squared curve, okay. I have just drawn the more accentuated curve here. So, I have 1 here, I have 2 here, I have 0 here, this is 1 and this is 4, right. So, I have 1 comma 1, I have 2 comma 4, and then if I do a straight line here, the slope of this straight line f of x naught plus h minus f of x naught divided by h, okay. So, that is why this is a very interesting quantity to look at, okay. So, how much the function changed and at what rate it changed, right. So, this is the rate of change of the function from x naught to x naught plus h. That is why I am dividing by this, alright. It is the slope of that straight line. So, all these things are important to note, and I have got 3 here, right. I can also look at it on the left side. On the left side, the function sort of decreases. In this case, in other cases it may increase. So, I am going to look at f of x naught minus f of x naught minus h, right. So, this is 1 and this x naught minus h, this becomes 0, isn't it? This is 1, this is 1. So, you end up being 0. So, that is 0. So, it is 1 minus 0, 1, okay. Now, to keep this similar to what I did for the right hand side, I will sort of rewrite this as f of x naught minus h minus f of x naught by minus h, and that will become 1. So, you see this is also the slope of the straight line joining 1 comma 1 with 0 comma 0, okay. So, that way I am measuring the slope on either side, which is sort of the rate of change, okay. So, you can also see that that is the slope, right. So, this guy, this straight line has slope f of x naught minus h minus f of x naught by 0 minus h, okay. So, I mean, you can write it so many other ways, so let me just write it as minus h. Okay, convince yourself that that's true. The slope of this guy is this one. I mean, if you want, you can also write it the other way around. F of x naught minus h by minus h. Okay, so by h, I'm sorry. Okay, in this case it will be 0 minus h, minus of minus h, it will become h. So these two are same. You understand? Hope you agree. These two are exactly the same. I'm just writing like this so that these two are exactly the same expression. This is with, you know, plus h, minus h, minus h. So you get the same expression on both the right hand side and the left hand side. Okay. So I'm tracking these two slopes, the slopes of these straight lines on the right hand side for the same step. Step equals 1. What is the slope on the right side? What is the slope on the left side? Of course, the curve took me to 2, 4. The curve took me to 0, 0. But I'm not going along the curve to find the slope. I'm just drawing a straight line here. Okay. That's what I did. I found the slope here. On the right hand side, there's a higher slope. Okay. So x square is just shooting off to the right hand side much faster. On the left hand side, there's a lower slope. It's going lesser. And that's like h equals 1. This h is very large at this point. Okay. Hopefully, it's clear what I'm saying. This zooming in is, I'm just zooming in at x naught equals 1 and looking on either side, right side, left side, and seeing how far I've gone for a particular step on right side, how far I've taken according to f of x, particular step on the left side, how far down I've gone, and just look at the straight line, do the slopes, you get this calculation. Okay. Now let's zoom in more. What is the meaning of zooming in more? Take a shorter step, right? Reduce the step size. So I'm going to make the step size 0.5, right? So it was 1 before, I'm making it 0.5. So notice this curve now, right? From 1, 1, I'm going to 0.5, 0.25, isn't it? And then 1.5, 2.25, right? So that's the square of 1.5. So I go from 1, 1 to 1.5, 2.25 on the right side with a step of 0.5 and go from 1, 1 to 0.5, 0.25 to the left side with a step of 0.5 to the left side. So now I can repeat the same calculation again. Okay, on the right side I had a jump of 1.25. I have to divide it by 0.5 now, right? That's how I get the slope. It's 2.5. The slope on the left hand side is 1.5. Okay, I got 0.75, right? You can do this subtraction. You get 1.5. Is that okay? So notice the previous thing had 3 and 1. This one has got 2.5 and 1.5. The slopes are getting closer now. Take a shorter step clearly, right? And you're not going too far. So the slopes are getting shorter. Okay, so let's zoom in more. Okay, 0.5 is still a sizable step. Let's take smaller steps. I'm going to take much smaller step, 0.125, and look at how this curve is starting to look. Okay, it's starting to straighten out, isn't it? Are you observing that? It's starting to straighten out. I mean, earlier we could see the curve. Now, once I've zoomed into this step of 0.125, right? 0.125, right? I'm from 1, I'm going to 0.875 on the left side. From 1, I'm going to 1.125 on the right side. There's corresponding values for the function itself. Okay. And if you compute the slope also, slope on the right hand side is 2.125. Slope on the left hand side is 1.875. You can do these calculations. It's very easy to do. And the most striking thing is how the curve is, how the line has, the curve looks almost like a straight line at this kind of zoom, right? 0.125 step zoomed in there. Okay, let's zoom a little bit more. In fact, you can keep on zooming. You can try this in Desmos to how much ever zoom that you like. But I've gone down to 0.0625. Okay, and I'm not showing you all the gory calculation. But for 0.0625, this pretty much is a straight line, right? Most people will look at this and say, why is this not a straight line? This is a straight line. This is really y equals x square. Nobody will believe that. They'll say at this zoom, like just 0.0625 on either side, it looks almost like a straight line. Okay, and then the slope calculation also, confirms that it is a straight line. Look at the slope on the left side is 1.9375, on the right side is 2.0625. It's really nothing, right? So the gap is very, very small. And as you keep reducing h further and further, these two are going to come closer and closer. And in fact, as we zoom in and tend h to 0 in the limit, like we do, then the graph is going to look like a straight line around x naught, and the slope on either side is going to tend to 2. Okay. Now, this picture I showed with f of x equals x squared, you can imagine for any graph that I draw, right, I've drawn it, you know, at some level I've drawn it. And then if I take one point, if I keep zooming, you're going to get a straight line at that point, right? I mean, if as long as the graph was continuously nicely drawn without any major, you know, things around it, this should happen. Okay. So how do you formalize this? The formalization of this leads to the definition of the derivative. Okay. So let me show you how the derivative is defined. Here's the formal definition. You can see all these terms that I introduced earlier are showing up here. Okay. We're going to define a derivative of a function and this notion of differentiability. It turns out derivative always does not exist. There are cases where it doesn't exist. We will see that also. Wherever it exists, you can compute. Okay. It has a definition using limits. You remember limits of functions. Here also it's a limit of function. Okay. So let me show you, but it's not directly limit of f. Okay. There's a slight twist here. What is the twist? We'll see this. A function f is said to have a derivative L at a point x0 if the following holds. What is this following? Limit as h tends to 0. So there is a function of h here. What is the function of h? What we saw before, the slope, right? F of x0 plus h minus h x0 divided by h. Now this h need not be positive. Okay, it can be negative also. So it covers the right side slope or the left side slope, right? Limit as h tends to 0. F of x0 plus h minus f of x0 divided by h, that needs to be equal to this L. If this limit exists, right, when I say this limit is equal to L, this limit has to exist. If this limit does not exist, then the derivative does not exist, isn't it? We also know limits may not exist, right? All the time we don't have limits existing. Now, a couple of other things I want to quickly point out. Is this a function of what? This is a function of what? This quantity here, okay? Of course, this x0 shows up here, but I've fixed x0. x0 is a fixed value for me. This is actually a function of h. Okay, this guy, this whole guy, even though f and all is showing up here, it's tempting to say it's a function of x0 and all that. It's also a function of x0, but in this particular case, I've fixed x0. I'm thinking of x0 as a fixed value and I'm making h vary. So this guy is actually a function of h. Okay, and as limit h tends to 0, if I evaluate this and if this limit exists, we know of limits for functions, isn't it? We've seen that in prior classes. If this limit exists, then that limiting value is called the derivative of the function. Okay, I hope this definition is clear. There's lots of things here. It's sort of similar to the limit definition, but a slightly different way to define derivative. Okay, now there's notation. There's multiple notations for derivatives. I'm going to start with this notation. I'll use the other notations later on as needed. Okay. The notation I'm going to say here is f prime of x0. Okay, so this quantity, this limit, this derivative, whenever it exists, I'm going to call it f prime of x0. So this is derivative, f prime of x0 is the derivative of f at x0. Okay, whenever it exists. Okay, of course it may not exist. So this is the derivative. Why this notation? Why is this f prime? Why this f? Why do I think of the derivative as a function? Okay, we will see that later on. But for now, we can keep this as a notation. Okay, so this notation works in this fashion. Okay, now what is differentiability? You can imagine the very easy the extension that comes, right? A function f is said to be differentiable at x0 if f prime of x0 exists. Okay, if this limit exists, then it is called differentiable. Okay, so simple definitions, and you see the motivation of this definition, right? Any function which is reasonably smooth in some sense, very smooth, very smooth in some sense. As you zoom into a point, it should become like a straight line. And what is the slope of that straight line, right? That is sort of this calculation of the derivative and differentiability. Okay, and this seems like a difficult calculation. Okay, we will simplify it later on, but for now let's just accept it and look at the connection between this and the slope of the straight line, and that itself will tell us a lot of very interesting things. Okay, simple enough definition. I hope that you appreciate this. Okay, so let's compute the derivative. We have a definition. Let's compute the derivative of f of x equals x square. We already saw that example in the zooming in part, right? Let's go ahead and compute it. Okay, we know how to do this, right? We've been computing limits all along. How hard can this be? It's just a rational function of h, isn't it? Right? x0 plus h whole squared, f of x plus h, f of x0 plus h, right? x0 plus h whole squared minus x0 square divided by h. you simplify this, right? X naught square will cancel, isn't it? You will get x naught square plus 2 x naught h plus h square minus x naught square. So, this x naught square will cancel and you just get this and divided by h. And notice this h is there in both the terms and you can cancel and you will get 2 x naught plus h. Okay. So, this sort of complicated looking function ended up becoming 2 x naught plus h. Very simple simplification. Do you see that for x squared? Okay. So, once you see this, very easy to write the derivative of f at x naught as limit as h tending to 0 of this guy, which is same as limit as h tending to 0 of 2 x naught plus h, and that is just 2 x naught. Okay. Look at that, we are able to easily use the definition and compute the derivative of a function. Okay. For simple functions like x squared, this derivative ends up being very nice. So, you see now why there is motivation to write it as f prime of x, right. So, you see you get 2 x naught. So, its derivative is a function of x naught, right. So, we will explore this a little bit later, but anyway. So, this is the derivative for x squared. Okay. So, what does this really mean in terms of the shape of the graph, in terms of the graph on the graph graphically? What does it mean to say the derivative at x naught for x squared is 2 x naught? This is the meaning we have been after. If you zoom into f of x equals x square at x equal to x naught, the line through x naught comma x naught square, right? What is this x naught comma x naught square? So, that is the point on the curve at x naught comma x naught square and slope 2 x naught, right? The line has to pass through this point and it should have slope 2 x naught. If these two conditions are satisfied, that line is what you will get when you zoom into f of x equals x square at x equals x naught. Okay, I hope that is clear. So, let me repeat that once again. If you go to f of x equals x square at x equals x naught and keep on zooming in, we know we are going to get a line. That line passes through x naught comma x naught square, right? That is the center of that line. What will be its slope? Its slope will be 2 x naught. Okay. So, let me illustrate this once again for you. This is this orange sort of line is the curve is the y equals x squared. I have drawn these lines. So, here is a line passing through 0.5 comma 0.25, okay, and the slope is going to be 1, right, 0.5 2 x naught, and that is that line. You see this line, as you zoom in you are going to get this line. Likewise, this green line is at 1 comma 1, there is slope 2, okay, and you can see as you zoom in here you will get that. At minus 1, right, minus 0.5, I am sorry, x naught equals minus 0.5, slope is going to be minus 1, and there is that sort of orangish, okay, the curve is red, I guess. This is the orange line here, this slope, and then you have minus 2 at x naught equals minus 1, and this slope of minus 2 here, this black line passes through this point. Okay. So, by the way, I am not sure if we saw the formula for straight line passing through a point with a particular slope. It can be quite easily derived. It passes through one point, it has a certain slope, right. So, y equals mx plus c, m is given and it passes through one point. So, you can find c also, right. So, it is a very easy problem to solve to get this line. Okay. So, you can plot this in Desmos. You can play around this with Desmos. In fact, you can do nice animations of these line moving along the curve, and that is a nice thing to see. Okay. So, hopefully you visualize this. So, I have computed the derivative and I am able to see it on the graph. Okay. So, let us push this a little bit further just to show you what is the slope of this tangent line and the derivative. Here you have a function, and I have just sort of shown you at different points how these lines could look like. Okay. So, basically you draw a straight line that approximates the zoomed in f of x at x naught, and you end up getting a line tangential sort of to f of x at x naught comma f of x naught, and if the slope is straight on both sides, same on both sides, the derivative becomes the slope of that line, right. So, that is the way in which to graphically sort of compute the derivative. You zoom in on a point, and if you get a straight line, then you are done, right. The slope of that guy is the derivative. Okay. So, here is an example to show you where derivative may not exist. There are two examples here. One is this is a function f of x which has a discontinuity at a, okay, a jump discontinuity. It comes here, it jumps, and then at b it does not have a discontinuity, but it has a change of slope. There is a sharp change of slope. There is like a corner. These things are called corners. So, this function has a corner here. Okay, at a there is a jump discontinuity, At b, there is no discontinuity. The function is actually continuous at b, right? If you come to the left or come through the right, you end up at the same point. Function is continuous, but still this is a bit jerky, isn't it? It's like some sharp change of direction is happening. There's a corner here, okay? So it turns out at a and b, the derivative does not exist, okay? So at a, it is discontinuous. Clearly, derivative won't exist. If you come here and this f of x is here, it's not taking a value here. It will not work at all. So if it's discontinuous, the derivative won't exist. So at a, it won't exist. At b, also the derivative won't exist. Why is that? If you keep zooming into this point, the slope of the left side will always be 0. The slope on the right side will be, maybe 1. I think the slope is 1. So you have a slope of 1 here on the right side, slope of 0 here on the left side. So these two will not become one straight line. There will be two straight lines all the time because of that corner. So both at a and b, the derivative does not exist. Okay. So this is something very, very interesting. So when you look at the graph of a function f that is plotted, you can quickly identify these points. See, earlier we were identifying points where the function has discontinuities, right, where it has jumps and all that. Now, additionally, you can identify places where the function is not differentiable. Okay, so just looking at the slope, is there a sharp change of slope, or is the curve going smoother? Okay, so those also, this derivative, existence of the derivative and differentiability will help you identify those kind of points, or at least characterize those kind of points. Okay, so this picture is sort of important, and you can use it in some problems. So here are the sort of problems where you may want to use it. So here is, so in these examples, I'm going to show you functions, and we're going to work out places where this function may be discontinuous. Okay, so the first function is discontinuous or not differentiable. Okay, both of these we'll see, continuity, differentiability. Let's look at a function like mod x. Mod x looks like this, right? This v function. Mod x is what? It's x for x positive and minus x for x negative. So it's always absolute value of x. So it will have this shape. Okay, think about why that is true. Why this f of x equals x for x positive. This is just y equals x line. And this guy is y equals minus x line, right? F of x is minus x for x negative. Okay, so just look at this using the previous graph. You can easily see there is only one point where the function is not differentiable. Okay, and that is this guy here. So let me put a red X here. It's not differentiable here. Okay, what about continuous? What about continuity? It's continuous everywhere. So this mod x is one function which has this very nice property. Not nice, I don't know, nice, not nice, you can decide. It is continuous everywhere, but it's not differentiable at 0. Okay, so that's the first graph here. So let's look at the next one. Here is this graph. Okay, I've just hand drawn it. It looks a little maybe not very proper, but anyway, so you can sort of roughly see this is the function. F of x is x squared for mod x less than 1 and equal to 2 for mod x. It doesn't say what to do for greater than or equal to, so maybe we'll take it as greater than or equal to here. Oops. This is greater than or equal to, okay. I hope you're okay with that. So let me just do this here. Okay. So at that point, it's so if you look at this, this function is also going to be continuous everywhere, right? There is no problem with continuity. Okay, so you can happily go through every point here. The function is continuous, but at this point and this point, it is not differentiable. You can see the differentiability problem, right? The slope on either side is not the same here. So here also the slope on either side are not the same. Okay, so you don't get one straight line as you zoom in. You will not get one straight line as you zoom in. So these 2 points are not differentiable. Okay, so it's continuous everywhere, but not differentiable at x equals 1, x equals minus 1. Okay, so that's the point. Here's another picture here. This is this complicated looking graph. Let's make sure it makes sense. So the f of x is x power 7. So this is x power 7. Okay. Do you agree it's x power 7? It could be x power 7, right? It's increasing like that. and on the negative side it's got this odd symmetry, it's just flipped around symmetry, it comes back here, okay, for mod x less than 1, and it is -1 for mod x greater than or equal to 1, okay. So, greater than or equal to 1, it's -1, so you have to put a like a circle here and a solid circle here to illustrate, to bring out the point that at that point the function takes a value -1 and not +1, okay. So, for this guy, first thing is you have to find the points where the function is not continuous, this guy, right, this point here, maybe I will use another thing here, green I will use. So, this point, it is not continuous. Once it is not continuous, no point in thinking about derivatives, okay. So, something is not continuous itself, you zoom in, what will happen? How will you get a straight line on both sides? It's just simply not possible, right. So, you do not have to bother about points where it is not continuous. So, that green is basically point where it is not continuous itself, but still that is not the only place where it is not differentiable, right. Everywhere else it seems okay, but then there is like this little problem here, right. So, here also this guy will be not differentiable, no, I mean of course this x equals -1. So, x equals -1, the function is not differentiable because the slope here clearly varies sharply from the slope there, okay. Okay, here is a much more complicated function, okay, to motivate why you need all these notions very carefully, okay. So, look at this function here. So, let us first focus at mod x less than 1. It is mod x power 1 by 5. It is not just mod x, it is mod x power 1 by 5. What is x power 1 by 5? X power 1 by 5 is going to sort of look like this, isn't it? It will start like that, sharply up and go off to infinity in this direction. Mod x power 1 by 5 will be symmetric. I think my picture here maybe is not quite symmetric, forgive me for that, but it has to be symmetric, okay. From +1 onwards, it is this x by 5 plus 4 by 5. Okay, you can plot it, it looks like that. For x less than or equal to -1, I have put -x here. So, it goes off in that direction. So, if you see here, there are a few issues, okay. So, let us look at x equals 0. At x equals 0, you have a problem, right. The slope, do you have a problem? Think about this, okay. So, what happens at x equals 0? So, if you go to the right side or the left side, it turns out the function has some sort of an infinite slope. It's almost vertical. Okay, so if you zoom in, you're going to get a vertical line. Okay, that line has an infinity slope, right? So the limit is sort of going off to infinity in some sense. Okay, so at that point, it's got a infinite sort of slope. So we're a little worried about what to do there. We don't know. We have not seen such situations in great detail. We'll see later on some more situations like this and what to do. So technically, I guess if the limit is infinite, we say it diverges. We don't say it converges, etc. So the limit doesn't exist. So here at this point, one could say limit is infinity and it's plus infinity in both sides. So maybe people will argue something, but it's really not a very nice point to see. Okay. The other point where you can clearly see a change in slope is this point, right, at -1. And the plot itself, it's graphically very evident that this one has got a change in slope. Another point which is a little confusing is x equals +1. What is going on here? Okay, what is going on at x equals +1? Okay, so it's x power 1 by 5 on the left side and it is x by 5 plus 4 by 5 on the right side. Graphically, it looks like the slope is the same in both sides. Okay, it's continuous, all right, but graphically it seems to look like the slope is the same on both sides, but we cannot conclude much from that, right? We need to analytically compute the slope, right, the limit on this side and the limit on that side. As you do this, properly compute the derivative and confirm that the derivative exists for a curve like this. Okay, so we need methods to analytically compute derivatives. Only then we can be sure about these kind of places, these kind of points, and what to do about them. Okay, so graphically you can go reasonable. You can consider reasonable number of functions graphically to figure out whether they are differentiable or not. But when it gets to situations like this, there can be some situations where an analytical way to compute derivative also becomes very, very important. Okay. So, to summarize, we have covered a lot of ground in this lecture. We defined the derivative, we computed it for a very simple example like x squared. More importantly, we saw the graphical connection. What does the derivative mean? What does the derivative mean at any point, right? If you zoom in, the slope of the line, if it is a proper line, then that is the derivative. And that gives you a lot of ways in which to graphically, visually see and figure out where the derivative may not exist, okay, where the function will not be differentiable, okay. So, you can see that little bit, but that alone is not enough. You need analytical ways to compute the derivative, and that is what we will see in the next lecture. Thank you.